that part. So I heard that Donghui Ma is online. Welcome.
Yes, I'm here.
Yeah, we can hear you. Can you hear us?
Yes, I can hear you.
Yeah, then we can start.
Okay. Good morning, everyone. Glad to be here virtually, and I feel pity that I can't present in person, but I hope this makes my carbon footprint lower and make this symposium greener than necessary. Today, I'm going to talk about the breeding progress in terms of carbon footprint reduction for 5 major cereal crops in Germany. This has been some joint work with my colleagues in the past few months. We all know that the global food system major contributor to the greenhouse gas emission, and green agriculture production accounts for approximately 80% of total food system emissions. What we can do is to optimize agriculture management practices and reduce emission as much as necessary or possible. But we also have a question of what is the role of plant breeding besides its achievement of food security, especially when we have food security challenges together with this climate change challenge twinkled together. So the aim and scope of this research is to evaluate the greenhouse gas emission of cereal crop production to calculate their carbon footprints in terms of by means of life cycle assessment. And after conducting the life cycle assessment, we developed some new metrics. We can call it also some possible traits. And we also want to disentangle the genetic and non-genetic traits based on some statistical models. Doing this, we could assess the breeding's contribution to the climate mitigation in terms of carbon footprint reduction. And I will use winter wheat and winter rye to illustrate the main pattern for these 5 crops because some of the patterns are repetitive. We also could suggest that this new metric could be used for variety recommendation, if not directly for selection yet. We use also the VCU data. I think we have a few other presentations talking about the testing structure of European crops. And here we use the German Federal Office for Variety Registration, the VCU data from 1991 to 2021, which is 39 years of data. We use the post-registration population, means that all the varieties here in the data are after 3 years of testing, and they are approved. And then the management of the trials follow this good local agricultural practice in the major crop production regions across Germany. To conduct a life cycle assessment, we have such system boundaries. And you can see we have upstream emissions, the input of all this machinery, seeds, fertilizer, pesticides for the crop. We also have the on-field emissions, including the fuel emission. Here we have all these tillages, depends on the soil and all these different characters of the farm. We also have the sowing, fertilizing, pesticides, and harvest. It depends on the yield. So that's all the fuel emissions consumed. We also calculated the N2O emissions, fertilizer, caused by fertilizer and crop residues using the IPCC guidelines. We concluded at the farm gate, that means the downstream emission will only include the transport emissions. We defined or we used the 2 functional units or 2 metrics, which is the total greenhouse gas emission per unit land area. That's the upstream emission plus the on-field emission plus the downstream emission here. The other metric is the carbon footprint, which is the total emission divided by yield, which is the kg of CO2 equivalent per unit kilogram of products. After getting these 2 additional metrics, the total emission per land area and also the carbon footprints together with yield, we borrowed this model from Laidig and also from Piepho for disentangling the genetic and non-genetic traits. After fitting the basic model, the full model, we also further regress. We have further regression for the genetic effects and also the year effect, using the genotypic effect modeled as the year of release for the variety, and also the year effect is modeled with gamma as the year of harvest effects. And by using this model, we could show this genetic and non-genetic trends separately. Before we have a look of the results, we can have a look of our yield or raw data in terms of location mean in the slide. And this kind of stagnation or kind of like plateau of yield for cereal crops is observed, I think, not only in Germany, but also in France. Maybe 10 years ago, they reached 10 years before 2013, they observed this plateau already, so around the year 2000. But in Germany, you can see that 2013, you have, we seem to like reach a plateau with this broken leg regression. And also for rye, we can see it is about like 2009. We have a similar kind of like plateau for yield. And this is observed also in Switzerland, I think, from our presentation, one of presentation yesterday. When we look at the results after fitting this mixed model to disentangle genetic and non-genetic traits, we can see that the genetic part is all increasing. So there is a persistent genetic gain for all these crops. Here there are more lines than 5 crops because I separated the barley and also some of the rye, like population rye or hybrid rye. So there are more like lines, but you could see that for the yield, the genetic gain is persistent. But for the E and M interaction, that's the non-genetic, or we could say this is the climate parts. This is like a downward trend when we fit this quadratic form of regression. So in terms of the total emission and carbon footprints, we could see that for winter wheat, the emission is like increasing. This is mainly driven by the yield, because if you have more yield, the way to calculate the emission and also all the input to achieve those yield will be increased. So that's expected. In terms of carbon footprint, we could see that this is also a persistent decrease of carbon footprint of production for winter wheat. For winter rye, we can also observe that the genetic trend for the greenhouse gas emission, the total emission is also increasing. The explanation is similar to the winter wheat. The actual mean of emission is showing a stagnation or downward change. And that's mainly also due to the yield development. And we could see that the increase of in terms of carbon footprints, we could see that the increase of non-genetic trend, the blue line, is upward, have an upward trend, and then the genetic trend has a downward trend for the carbon footprint. And these two forces just combined together will have this green line. That is the annual carbon footprint mean, which shows kind of stagnation too. So we may have a like a stable, relatively stable like carbon footprints in the near future, but this is a combined force from the rising of non-genetic trend and then downward trend of genetic trend. So that's the pattern we have for winter rye. And I forgot to mention that this pattern we have with winter wheat, we observed also for spring barley. And then this pattern we have for winter rye, we have it for winter triticale and winter barley. So that's the major pattern of genetic and non-genetic trend for yield, for greenhouse gas emissions per land area, and also for the carbon footprints. So although we observe this trend for the yield and also other metrics, we may have an overestimation of genetic trend due to aging effects, and we need independent vintage trial data, which we have, and we will add these parts in the near future for correction. And remember, we use the post-registration data, so we may have some other bias introduced. It is not the pure breeding progress or contribution, it is the registration data we have. So we need to also account these parts. And there are some other concerns from Raymond in the recent publication that we may introduce some further bias from including certain checks and other data points. That's something that we need to check. And there is also inherent bias we may introduce from the IPCC method to account for N2O. And here, different methods will get you quite different results, and we need to bear this in mind. The takeaway message is that although cereals may have yield plateau in the recent years, but the genetic improvement in yield persists, and the non-genetic effects in terms of yield are mostly negative. But genetic improvement obviously help to buffer the negative trends in E&M to maintain high yields. In terms of carbon footprints, the genetic effect is downward and could compensate the upward non-genetic effects for some cereals. And the breeding, we believe, we show that it does not only contribute to yield improvement, it is also a tool, and I think silently did already for climate mitigation to reduce carbon footprints. And I think in the breeding setting, this carbon footprints is maybe not necessary for using as a metric, because we defined all the treatments the same, and the major contributor for carbon footprint will be the yield. But I think for variety recommendations, if you want to further differentiate all these farms or varieties in different farm settings, and I think that's something interesting to show to the consumer, that this could be some metrics to consider. So I also thank the funding agency to make this work possible, and that's all for my presentation.
Thank you, Donghui. I'll allow one question for right now, otherwise we're going to the discussion afterwards. I see one question here.
Yes, hello, George van Voorn, Wageningen University. Thank you for your presentation. I have a question on the interpretation of the data. In how far do you think that maybe the existence of conservation, right? The farmers are getting older. Is there maybe a trend that's the result of conservative management practice, for instance?
I'm not sure whether I understand your question, but I think younger farmer may adopt new technologies. And then also there is another trend to consolidate a lot of farms. So maybe this make the farm operation more fuel efficient. And I think we should not only look at there are two metrics. One is the total emission, the other is the carbon footprint. So if you only look at the total emission per land area, you could have a very poor farm, have very low emission. But then if you sell this product to the value chain, to the next user of the product, the carbon footprint might be very high. So I think with this transition of younger farmer or bigger farms, maybe we improve the carbon footprint in the future.
Okay, yeah, thanks.
Thank you, Donghui. Please stay for the discussion.